disk is treated as a file. Every device is treated as a file. And file system, right? File itself is a file. And file system itself is a device. And the file system device, it also has the same set of APIs. Okay? And so these, in Xenu, I think it's clear, you will see that the file system itself is registered as a device or pseudo device. It's not a real physical device, but it's registered as a pseudo device. And every file in the file system is also registered as a pseudo device in Xenu. Everything else, I think, in this slide, we have explained it in the high-level file system slides that we used before. But the only thing that is different, that worth highlighting is that everything is a device, or every device is a file. So they are the same. So everything is a byte stream. Okay. So a file is a byte stream. The file system itself is also registered as a device that can be manipulated as a byte stream. We will see. Right. So if there's one thing that you want to take away from this lecture, right, that is it. Right? So all the devices, all the files, and file system itself, they are all treated as a byte stream. Okay. All right. So we'll go through the slides again, and most of it I think you will be familiar because we have explained them in the high-level file system lecture. But let's still go through it. The purpose of file system, right? Why do you even need a file system? Right? And I think in the very early days, you don't have a file system. Right? What do you have? Can you imagine what you have in the very, very early days, right? When you use punch card machines to do calculation. So the data that you want to store, they are written on the punch cards. Right? Just numbers written on the punch cards. Okay? And the program is also on the punch card, and the program on the punch card guides you to read to the location, some location in the same punch card somewhere else, right? To read some piece of data, a number. Okay. All right, and then later, as you have more advanced machines, you have a storage device, and then when you have a storage device, that's when naturally people need to consider, right? How do I divide this storage device, such as hard disk, to store my data? Okay. And naturally, right, people mimic what human has been doing throughout the history, and because we as human, before we have computers, we store the data using files. Right? We write books, we write documents, we write letters, and all of these are files. Right? And so in the very early days, a file system is designed to mimic humans, how humans store files in history. Okay, and of course, in the very early days, you might not have this structured directory file, this kind of structured tree structured file system. You just have a flat file system which has a bunch of files on disk. But gradually, right, so it evolves into this tree structured file system. Okay, so purpose of file system, again, right, store data. And because we, in the beginning, we want to mimic how humans store data naturally, and it becomes a file system. Right. And the metadata associated with the file, right, contain the size, ownership, access rights, location on the storage system. Okay. So how to use a file system, right? So it allows the application to read and write data to files on local storage, and so the but it's not that easy, right? Because you need to allow sharing on multi-user system, handle caching, and manage a distributed file system that allows applications on many computers. Right? So these are more advanced, but some of them are not even unique to computer system. You can imagine that in a library, right? So library is you can consider it as a file system. You also have this concurrency or sharing problem. You have multiple users that want to borrow the same book, right? And you need to synchronize among them and to make sure some of them can borrow the book until maybe keep it for 2 weeks and need to return it, so that that user cannot keep the book forever and stop other users. Okay? So even in the library, this kind of human file system, you still have many of these similar problems. Okay, but in computer system, right? So because these processes or every user's program runs very fast, so the solution becomes trickier. Okay, control sharing on the multi-user system and caching, right? So sometimes you want to allow files to be cached on the local machine, right? If you have a remote file system, for example. Right? And when you have a distributed file system, this problem gets very complicated. Okay. Right. Yeah. Sharing is difficult. Right? One of the most difficult aspects of sharing revolves around the semantics of concurrent access. We already explained this. Right? Even in a library, this kind of sharing is not trivial. Okay. We will skip this problem for now. Just think about a few high-level questions. Right? What happens if a file is deleted after it has been opened? Right? You can have multiple processes, multiple users opening the file. Maybe both of them are just reading the file. Okay, but one of them decided, okay, I have finished reading this file, I want to delete it. Okay. And what happens? Okay, and you have many solutions to this. Right? Sometimes in some system this delete will just be blocked, right? So or it will fail. Right? So if you are deleting and someone else is using the file, I'll just give you an arrow and you just fail. And that happens in some systems. In some other systems, the delete is delayed. Right? So you issue a delete request, and the delete is only really completed after the other processes finish reading the file. Okay. It's up to each system to define what is the semantic the system wants to provide. Okay. Files permissions change after a file has been opened. Right? That is also possible. Right? Maybe I have a root user and a normal user. Both of them open a file. Okay, and while the normal user is reading this file, the root user might decide, okay, this file should be classified. I need to increase the permission of this file so that other regular users cannot read it. Okay, and it bumps up the permission of this file. And now what happens to the regular user? How to enforce that this regular user cannot continue reading the file. Okay, the file is moved to a new directory after it has been opened. This can also happen. File ownership changes after a file has been opened. This can all happen when you have multiple users opening the file. What happens to the file position in open files after a fork? Right? When you use fork to duplicate the process, what happens? Okay, and what happens if two processes open a file concurrently and write data? to different locations or to the same location. Concurrency, right, is almost has been almost always the most difficult problem to address in computer systems. And we have different forms of concurrency, and they are very, very difficult to address. Okay, so sometimes you might think it's adding. It might not be obvious why it's so difficult. Right? So later we'll see. Right? So in a lecture about multi-core system, you can see that adding multiple computer CPU cores to a machine makes the problem, the design of operating system, much harder. Okay. All right. So some design in most modern operating system follows these rules. For permissions are only checked when the file is open. Okay, so during the processing of a file, they are not checked. And each process has its own position for a file. Right? Every process has remembers the location of its read and write, the current location in the file. Okay, so it can continue reading from that location or write from that to that location. Okay, if two processes access the same file, changing the position in one does not affect the position in the other. Right? So these two processes can read the file at different locations. Okay. In Unix, a file is separate from the directory entry for the file. Right? So we have explained this. A file is represented using the inode data structure, and directory entry is different. Right? Directory entry has a file name and a pointer to the inode. Okay, because of this design, removing a file from a directory does not delete the file itself, right? Because there might be multiple directory entries linking to the same inode. Okay, so if you're only removing the directory entry, it does not necessarily delete that file's inode and the file's content. Okay, right. So when the file is removed, the actual deletion is deferred until the last process that has opened the file when it closes it. Okay, so every open operation will increase there will be a counter in each file, and it remembers what are the processes that are open this file. Okay, so yeah, only after all the processes open the file, closes the file, finish their operation, that's when a delete can really be performed. Right. And I think don't confuse this with the other scenario I mentioned in the first bullet point. Right. In the first bullet point, I was saying that removing a file from directory does not delete the file itself if there are multiple directory entries pointing to the same file. Okay. But here, the second bullet point is saying that there are multiple processes. Right? Maybe there's only one file and one directory entry, but there are multiple processes that have opened up this file. Okay. So, if all of them have closed the file, that's when the directory entry itself can be removed. So after all the processes close the file, that's when the directory entry is removed. If the directory entry is the only directory entry referencing this inode, that's when this file can be really deleted. Okay. So these are the two different levels of a delete operation. A file system can have multiple partitions, right? And sometimes they are called modules. So the idea is that you divide a physical disk into multiple areas and place a separate independent file system in each area. So in the very early days, if you're using Windows machine, you have a C, disk C, disk V, right? So this kind of a this that's a partition in Windows, right? And you are, I'm not sure whether currently Windows 10 or Windows 11 still uses a file system partition structure. Okay? But in the old days, you were recommended to install the Windows OS in C, disk C, and in other disks, you are encouraged to put your own data and programs in the remaining disks. Okay. Okay. So yeah, you have a way to link all the partitions together into a single unified hierarchy, and that is by using Unix mount. Okay. The advantage is higher reliability, right? So and lower maintenance cost. Okay. Right. So the disadvantage is the partition size must be selected when the disk is formatted. Okay. Yeah. So because you partition a disk into multiple volumes or partitions, each partition can have a much smaller file system. But the downside is that when you are formatting a disk, you need to decide what is the size of each partition. I think some of the latest file system allow you to adjust the partition size dynamically. Right? If there are some available disk space, you are able to adjust it dynamically. But that's more recent file system. Okay. For the older file system, you cannot change it. When the disk is formatted, you decide the number of partitions and the size of each partition. Okay. Right. Yeah. So yeah, you might have a file system, a disk that has two partitions. One is a root partition, the other is the user file system. Okay, and it contains all the user directories and user programs. And you mount this partition under this root user, this directory. Okay. Yeah, so this is the hierarchy of a file system. You have a file naming scheme. So in different operating systems, they might have different naming conventions. And you have a directory access, which uses its file names and its absolute path to traverse the directory structure and to access directories and then find the file that you really want to access. And then when you get the file, below that you need to, because the file is stored on the storage device, right? You need to use a disk device driver to really read the data and write the data. Okay, and at the lowest level is the disk hardware, which is manipulated by the device driver. Yeah, so naming level, right? So it deals with name syntax. I'm not sure whether, I think the, yeah, I think even nowadays, right? So Windows and Linux and Unix-based system, the file path is specified using different symbols. Right? So yeah, I haven't been using Windows for a while. I don't know its current status, but at least when I maybe like a few years back, I remember their absolute path is specified in different ways. Right? And also in Unix, you have a length limit of the file name. every file name has a length limit. I forgot exactly what it is. Maybe it's 256 bytes, if I remember correctly. You can try it out, but there is a limit of the length for each file name. Okay, so that's an example of the naming convention. And directory access, file access, disk driver, we actually have already studied all of them. Okay. So directory access and file access, we have explained them in the generic file system that slides. How the file system's tree structure is organized, and when you are accessing a file, how do you traverse this tree structure to find the file? And in order to do that, you need to access the directories and then access the file. Okay. So we have explained all of this, and disk driver. We also explained this how device driver is designed in our previous lecture. So we won't go into the detail. Okay. So two types of philosophy, right, to design the file system. One is called typed file. Right? The OS defines a set of types that specify the file format and contents. Right? And the user chooses the type when creating file. The type determines the operations that are allowed. Right? You can imagine, right? So movie files, video files, and photo files, and text files, they look very different. So naturally, you might want to give them different types and define different operations for them. Okay? But later people find that treating all the files as untyped at first, and then build on top of these untyped file operations, that is actually a much cleaner way to design file system. Right? Every file is just a sequence of bytes, a byte stream. Right? And the OS does not understand the contents, format, or structure, so only a small set of operations apply to all files. Right? If it's a sequence of bytes, the operation is the same as a device operation. Open it, read some bytes, write some bytes at some location, and close this sequence of bytes. Okay, and each type of files, like movie and photo, and those file type specific operations are built on top of these generic APIs. All right. So the pros of typed system, right? The types protect user from application file mismatch, right? So you cannot open a movie file using a text editor, for example. Right? You can have this kind of protection. Right? And file access mechanism can be optimized, and a programmer can choose whichever file representation the best for given need. But the disadvantage is that the types may not match new applications, right? And it's extremely difficult to add a new file type, so no generic commands can be written. You can imagine that almost every file format that you have been using in our computer, they evolve all the time. The photo format, the video format, right? They change. Although recently they don't change that much, but they change every year slightly. Okay, yeah. So it's very difficult to add to improve, change these existing file types and add new file types. Yeah. So that's a disadvantage. Okay. And on the other hand, the untyped files used by Unix, right, they have an advantage that it permits generic commands and tools to be used. Okay, if every file is treated as a byte stream, right, and then you can design a unified API that you can use to manipulate all files. And then the file system design is separate from the applications and structure of data they use, and there's no need to change the operating system. The new application need a different file format. Okay? So essentially, from the operating system's perspective, all the files are just a sequence of bytes. But from application's perspective, they could view this sequence of bytes differently. If you have a movie player, a video player, the video player could view this file as a video. Although it could run into errors, right? If you use it to play a text file, it will run into errors. But from the application perspective, it can choose to view this file according to its its expectation. Okay. So a text, you can. I think most people might have tried. You can use a text editor to open a photo. Right? You can use text editor to open a movie file. Although the content will be you cannot really tell what it is, right? So if you use text editor to open the movie file, it's going to be a random code everywhere. But you can do that. And that just shows you that from user application's perspective, they choose how they interpret a byte stream of the file. But from OS perspective, it just treats every file as a sequence of bytes. Okay. I was thinking some example that might better explain this. So can you imagine if the OS need to consider different types of files and provide special support for different types of files in the file system itself? Right? What are the examples? Right? How it would complicate the OS itself? I think maybe movie or video file and the text file, these two could be a good example. So you can imagine that to store large movie files, you might want to compress it. And it could be true that these movie files, they are highly compressible, because you can imagine every movie file is a sequence of video frames, and the adjacent video frames might be very similar to each other. Right? So these video files, they have this characteristic. They are very huge, but they are also highly compressible. Text file, on the other hand, is very different. Right? So your human written text, at least they are not that compressible as a video file. Okay, so the text that you're writing can be very different in every line. Right? So they are less compressible, but the file size should be much smaller than the video file size. Okay, and then your file system might need to support, right? If it wants to support efficient storage and retrieval of these two types of files. Right? So it will add a lot of complexity in the file system itself. Okay. So that's a benefit of using untyped files untyped files. The OS treats all files the same, a sequence of bytes, and it does not need to support different files differently. So the OS stays reliable. Okay. The consequence, right? The downside is that OS cannot prevent the mismatch errors. Right? right? So right, so that's why you can use text editor to read a video file, because OS does not care, right, what the user program expects the file type to be. It will allow you to use a text editor to read a movie file. The OS does not care, okay? And the file system may not be optimal for any particular application. Like as we mentioned, the file system treats all files the same. It won't try to use a compressed movie file using special compression algorithm, right? Yeah. So it may not be optimal for different type of applications. Okay, and the operating system owner does not know how files are being used. Okay, right. So you can imagine that the movie files are usually used in a sequential read, this kind of format. It's less likely to be edited. Most likely it's just a read in a sequential way. If you know this access pattern for movie files, the OS can provide a much efficient access to movie files. All right, now let's look at the generic operations of untyped files. Right, now you will see it's almost the same as the device APIs that we studied in the previous lecture. Right, so you can create a file and you can delete. Right, they call it destroy here, but you can delete this file and you can open it, you can close it, right? You can read it, you can write it, and you can seek to move the location, and you can control. This is exactly the same, right? Except for the destroy, the name is different. This is exactly the same as the set of APIs that you have seen for device drivers. And the reason is that each file is viewed as a sequence of bytes. Each device is also viewed as a sequence of bytes. Okay. Yeah. And also the same way as we explained before, actually, this control. Everything else is standard, but a lot of the ad hoc operations are hidden in this control operation. Okay. File allocation, we already explained this in the generic file system, so we won't go into this in detail. So we won't explain those again because we have explained them in the generic file system, but we'll quickly go through Xenu's file system. Okay. Yeah. So we assume that there is one file system per disk, and the underlying disk is an array of 512 byte blocks. And so the simple approach Xenu takes is divides the disk into three areas. You have a directory area, and which only has one block. You have a file index area, which has a small number of blocks, and you have data area, the remaining part of the disk. Right? So this is a block 0. It has right. It's the directory area. This is the index area, and this is a block area, the data area. So this is a simple file system that Xenu already has. It's much simpler than the inode based file system that we have explained in the generic file system course. But in your lab, right, you will modify this simple file system to be more advanced version, to use inodes. Okay. Right, so the size of the index and data areas is chosen, the data disk is formatted, so it's predefined. Yeah, so the file system treats the entire data area as an array of data blocks. And this is similar to what we have explained before. And every file is just a linked list of data blocks. Okay, and the inode is a way for us to organize this linked list efficiently. Inside each file system, the data blocks are numbered from 0 to d minus 1, where d is the total number of data blocks. And each data block is 512 bytes long and occupies one physical disk block or one physical disk sector. Okay. So these are the details. I don't think we don't need to go through them in detail, but this is important, right? So the unused data blocks are linked on a free list on the disk. This is very similar to the free list in the memory management system of Xenu. So in the disk or file system, you also have a free list of all the free blocks. The index area, right, has an array of index blocks or I blocks. And inside the file system, these index blocks are numbered from 0 to I minus 1. These index blocks are used to store the index to the data blocks. Okay? All right. Yeah, so each index block is smaller than a physical disk block. Because an index block is smaller than a physical block, so multiple index blocks occupy one disk block. All right. And each index block stores the pointer to data blocks that make up a file and offset in the file of the first data byte that the index block indexes. Okay, so what is this index block? Let's take a step back. Remember that every file in Xenu is just a list of data blocks. Right? Okay, every file is a list of data blocks. And this index block is stores, right? For a given file, its index block stores the address or the index to its data blocks. Okay? Right, so that is the index block. Right. In the generic file system, we learned inode, right? In Unix and Linux, inode is used to represent the file, and the inode stores the references or the addresses to all of the file's data blocks. Here, this index block, right, is the simplified data structure, right? It's much simpler than inode. It's a simpler data structure that Xenu uses to store the references of the data blocks belonging to one file. Okay, very simple. So if a file has only one data block, it will have one index block, and inside this index block, it has an index pointing to that data block. That's it. Okay. Similarly, unused index blocks are linked on a free list on the disk. Right? You also have free I blocks. Right. Okay, and the file system has a directory area, and this directory area has an array of pairs. Right? File name, first index block for that file. Right? Directory entry. This is the directory entry structure that we explained in the generic file system lecture. Okay. Right. So conceptually, a file consists of a list of index blocks with pointers to the data blocks that contain the bytes of the file. Okay. And directory entry provides a mapping from a name to the index block list for the file. So the index block belonging to a file, they form a linked list. All right. Yeah. Yeah, so the location of the directory block is hard-coded in Xenu. Right? It's the first block on disk, and the directory is limited, the size is limited, but has a sufficient size for a small embedded system. Because it only has one block, so it's very small. You cannot create a large number of files. Okay. Right. So the Xenu file system looks like this. This is a directory block. It is the first block on the disk, and one entry in it, right? One directory entry in this block. It has a file name and has a pointer to the first index block belonging to this file. And this index block belonging to this file will form a linked list. Okay, and every index block has an array of index entries, where each index entry points to one data block on disk. And these data blocks, they form the real content of this file. Okay, so this is the simplified data structure that Xenu uses to implement its simple file system. All right. Okay, free list. A Xenu file system contains two free lists and all the index blocks that are not currently used for any files, right? And all the data blocks that are not used by any files. Okay. And the directory block contains pointers to these two free lists. Here, although we use pointers, but the pointer here is different from the pointer in memory. So in C language, pointer means a memory address. Here, this pointer means pointing to a block on the disk. Okay. Let me see. These details, I think the only thing that's important for your understanding is that here. So the diagram that we showed before, it looks like a linked list in memory, but it's actually a list on the disk. Every I block is a piece of data, is a block on the disk, and it stores a pointer. And that pointer points to another location on the disk. Right? So these linked list is not in memory. Okay, you can copy this data structure into memory and use it to traverse the blocks, but their real content is on disk. Okay. To find the data block for giving offset in the file system must work along the linked list of index blocks, which means reading items, these items into memory. So copy this list into memory. Okay. Yeah, so this is similar to inode. Within the operating system, a file is referenced by the I block number of the first index block, not by name. Right, so this is very similar to inode, the concept of inode. Okay, so this is essentially the first I block in the I block list belonging to this file. And this represents the file. Right, if you let's go to this. Right. For this file, what is it used to represent this file in OS? Well, this is a file. What is that in Xenu? What is used to represent this file? It has file name. Right.
represented as like device drivers?
Sorry?
Aren't files represented as like devices technically?
Yes, but that is true, right? So there is a pseudo device, pseudo file device in Linux. So I think that the point we want to make is that here the first I block, there is a list of I blocks, these blue blocks here. The first I block is used as a representation, as the identity of this file indeed. Right? If you find the reason is that if you find this block, this I block, you can retrieve all the content belonging to this file. Right? As long as you can find this I block, you don't even need the file name. Right? As long as you hold this, you know this I block, you can use it to traverse this list of I blocks and also find any data block that belong to this file. So yeah, for any file in Linux, the key is the first I block. Right? That is essentially equivalent to the inode that we have explained in the previous lecture. Right? So that's why the concept is explained here. So a file is referenced by the I block number of the first index block. That is equivalent to that file. A name is only needed when opening a file. Inside OS, they always use this I block number. All right, so now file access in Linux. Right? In Linux, everything is a device, or every device is a file. But I think whether you call it a device or a file, it doesn't matter that much. The core concept is a byte stream or sequence of bytes. Right? Both device and file, they are all modeled as a sequence of bytes. Okay. The file access use a set of file devices, actually let me. So yeah, the file system itself has a pseudo device. Right? So it's called a L file system. This is called the L file system because it's a local file system. In Linux, you have a local file system, you have a remote file system. Right? So this is a local file system. Right? This device is used to open files on the local file system. Right? It is registered as a device. Okay, and it has a set of key additional file pseudo devices that are used for data transfer. Right? So what does it mean? So this L file sys, it has an additional set of file devices, and each file device can be used to open a file. Okay. Right. So the device driver for data transfer pseudo device implements read-write operations. Okay. So the device driver for the file system device is L file system device only implements open and control. Because at file system level, you don't need much to do. Right? So in Linux, it's simplified, but the operation that you can perform on the file system, if you remember, what have you done anything at the file system level? I would say mount could be one operation that you perform for a file system. Right? You have a disk, you format it. Right? Format is another operation. Right? You after you format it, you can mount it to some location in the existing file system data structure. Right? You can also run FSAK. Right? So these are format, mount, FSAK. These are the typical operations that you can perform for a file system. Right? In Linux, it's simple. Right? You just have open and control. Okay. All right. file, the application calls open file system. Right? So you can this open will open a file if it exists. If it doesn't exist, I forgot. Let me think. Yeah, if it doesn't have the file does not exist, I forgot whether it returns an error or it will directly call create, right? Because there's a create file operation that you can invoke. Okay. All right. So this call sets a description, DSC, to the device descriptor of one of data transfer pseudo devices. So in the pseudo devices function list, there is an open function. Right? It's going to call that pseudo device's device-specific open function. Okay. And after this file is opened, the application can call read write and possibly seek, right? And to perform read and write of that file. Okay. When the finishes using the file, the application will call close. Right? This is the entire life cycle of the operations on the file. Open it with L file sys. That's how you open a file in the local file system, and you perform read and write using this L file system and the file system and the file descriptor, and then you close it. Okay, so this DSC returns the file that you want to manipulate. Okay. All right. Okay, so this is a lengthy explanation of how file is really accessed, but it's worth going through slowly. Right, so this will be the last thing that we explain. Yeah, this will be the last thing we explain in this lecture. But I hope that everyone try to follow this closely, right? So if you understand this process, you will understand how Xenus file system works step by step. Okay, it's slightly different from what we explained in the generic file system design, but it's still worthwhile to understand the detail. Okay, so. Yeah, if there are two things that you want to take away from this lecture, one is that everything is a file, everything is a byte stream. Second is this sequence of operations. Right? When in Xenu file system, when you access a file, what exactly are the things, are the steps that are performed? Okay, right. So when an application in Xenu opens the file, the code takes the following steps. It obtains a copy of the directory from disk if not already in memory. What does this mean? Remember that in Xenu you have a block, directory block on disk, right? And maybe this directory block was not even read into memory. So the file system exists, but the content of the directories are not in memory. So if they are not in memory, you need to read this entire block into memory. Right? This directory block contains the file name to iblock mapping. Right? So you need this directory block. Okay. So after you read this directory block from the disk, then you can search in this directory block to find the iblock number for the file. Why? Remember, this directory block contains a list of file name to iblock pairs. Right? File name to iblock number pairs. Right? So you're going to use the file name that you want to access to search in this list to find the pair that has your file name and the iblock number belonging to this file. You want to find that pair. Okay? Once you find that pair, you get the I block number for the file, or more precisely, this is the I block number of the first I block belonging to this file in this list. Okay? Right, so it is this one, right? The first blue box there. The first blue box is what you get here in the second step. Okay? Now, once you get this I block number for this file, you allocate a data transfer pseudo device for the application to use, right? So the remember that you have a list of pseudo device for file operation. Okay, those pseudo devices are not tied to any specific file. Right? Whenever a file is opened, if there's available pseudo device that are not used, it's going to bind them. Right? So that's when you bind this file that you just opened to that specific pseudo device. That pseudo device has a list of operations, read, write, file operations that you need to manipulate this file. Okay, right. So that's when you bind this data transfer pseudo device to this file. Okay, and you initialize the file position to 0, which means that I just open this file. My the current position I'm reading or writing from is the beginning of the file. Okay. All right. And yeah, so you obtain a data block that contains the byte 0 of the file. Right? You read yeah. If this is what you want to do, right? You want to read starting from the first block, right? First data block. If this is what you are trying to do, then you can read the first I block to find the first data block ID. What does this mean? Okay. This is the first I block. You need to load this I block from disk to memory, and then find the first item in this I block. Right? It's a list of block numbers. The first item is a block number. That block number points to this data block on disk. And then you go to the disk to read this data block to memory. Okay, that is how you read the first. That's how you read the first data block of this file. Right? Read the first I block into memory, find the first data block ID, which will be the first entry in the I block, right? And read the first data block into a buffer, into memory, right? And then set the byte pointer to the first byte in this buffer. So that's how you read the first byte that belongs to this file. Okay. All right. All right. So that is the simplest operation that you can perform, right? Reading the first data block belonging to the file, and there are some other operations. Right? The application could read or write data, and if the file position has moved to a new data block, you need to fetch the data block from disk. And you can imagine, when you read continuously, and you could finish reading the first block, the first data block of the file, and then you want to continue to read the second data block. Right? When you start reading the second data block, you need to find the index, the data block number of the second data block, and then go to the disk to read the second data block from disk to memory. Right. So that is what it is mean here. Right. So if the file position that you're reading from or writing to has moved to a new data block, you need to fetch that data block. Okay. And you can read or write the data from to the data in memory and incrementing the position for each byte. But remember, right, if you're writing to that data in memory, later you need to mark it as dirty and later write it back to disk. Okay, so every block in Xenu source code, if you read it, every block has a flag marking it as dirty or marking whether it's dirty. Okay. All right. Yeah. So only until the next data block is referenced, that's when you fetch the next block. So if you don't reference the next data block, the OS will not fetch it. Okay. All right. So the key points: a copy of the index block and one data block are kept in memory. So this is based on the assumption. This is a very simplified implementation. Right? In Xenu, you only keep one index block and one data block, right? Because it assumes that currently you are just operating one data block. You are either reading or writing. Reading one data block or writing to one data block. It does not keep multiple blocks in memory. Okay, and there is a pointer gives the address of the next byte to read from in the in-memory buffer and holds a copy of the current data block of the next byte to be read. Right? So there is a 1 byte, a very small buffer, right? 1 byte. It uses this buffer to read from the block's content and write to store the writes for that block content. Okay. Right. So the unit of read and write operation is byte, and the unit of block that Xenu keeps in memory is 1. Right? For each file, it only keeps 1 data block in memory at a time. Very simplified design. Okay. Let me see. All right. So we'll glimpse through some of the code, but you can read it in detail yourself. We won't really talk about the function, how it's executed step by step today. So this is the file system control block, right? Local LFLC BLK, right? So it means local file system C, right? C means control block. Right? That is the control block. And right, you can see that it has a LD entry, as this is the pointer to the directory, right? To the files entry in the directory block. Okay, so this is the pointer to the directory entry. Okay, LF name, right? This is the name of the file. Okay, and LF I number. This is the ID of the current index block. Right? Remember, there's only one index block and one data block in memory for each file. Okay, this is a I block, LF I block. This is the in-memory copy of the current index block. Okay, and this is the number of the current data block, and this is the in-memory copy of the current data block. Right? There's only one block. Right? This is just the block size, right? Because Xenu allows you to use different block size. Right? You have exactly one I block and one data block in Xenu. This is the byte buffer that you use to read from and write to this files block, and you have a dirty, right, marking whether this I block has been modified. You have this data block dirty flag marking whether the data block has been modified. And if they are modified, they need to be written back to disk. Okay. So this control block is very simple and straightforward. Right. And this is a getC is reading 1 byte. Right. It's a function reading 1 byte from and open the local file. Let me see. think we actually have time to go through this. Right? Okay, reading this one file, reading this 1 byte from this file. Right? So you have these directories, you have the directory entry for this file, okay, and you need to get its control block, okay, and this is the next data byte in that file. Okay. So you use this this is to get a device, right? Remember that this is used to store the open file table entry, right? And then use this directory entries pointer to find this open files table entry. Right? We did not show the open file table here, so it might be hard to understand. But you can read this open file table in Linux source code, right, to understand how this works, right? So this LFL tag. Okay. Yeah, you have a log to protect this file, right? In case there are multiple users who want to access this file, okay? And you check whether the file is opened. Okay. Yeah, check the size. Right. This is so this is an interesting operation here. Okay, which let me see. Yeah, we won't be able to go to because this LF setup. I'm not sure whether people have read this function. Right? How many of you have read this function? LF setup, this function. Some of you, right? It's not trivial. Right? So I think we won't be able to explain how this function works in detail because this LF setup is actually quite complicated in Linux. Right? It checks whether the current read or write position has exceeded the limit, the boundary of this current block, and if it exceeds the boundary of the block, it needs to check whether the current block is dirty or not. If so, it writes it back, and then after that, it needs to load the next block to memory. If also the current index block is also finished, right? You also exceed the boundary of the current index block. You also need to load the next index block. Right? So this LF setup does a lot behind the scene. Read this LF setup function if you haven't. Okay. Right. So this is to set up. If the byte pointer is beyond the current data block, you need to set up a new data block. Right? This is not trivial. Okay, and this is a read. Right? So this is the real read is very easy. Right? Extract the next byte from the block. Okay, updating the file position and return the byte to the caller. Why it extract the next block like this, right? Because this LF byte, this is a pointer into the data block in memory. This LF byte is a pointer to the current data block of this file in memory. It points to a location in that data block. And you use this to extract 1 byte from that data block. Okay? The read is very simple, reading 1 byte. And after read it, you increase the position, and then you signal as saying that I finished reading this 1 byte. Okay, reading is very simple. Right? The really the complicated part of the implementation is in this LF setup. Right? You read the LF setup yourself after the lecture. Okay. All right, that's it for today. If you have answer questions, come up and write them in.